Student, so today we want to look at continuity. In fact, we want to look at when do we say a function is continuous. That's what we want to look into today. So hoping that you have already grasped the concept of limit, and continuity is going to build on that. So let's go into continuity straight away. So what we have seen previously is that you can evaluate the value of the function as x approaches a. And we know that there are some functions which you can straight away do direct substitution and then calculate the value of that function at x. In functions of this type, so we will say that a function is continuous at a point a. That means the limit of f of x as x approaches a is exactly the same as the value of that function at that point. In fact, a definition is here where we say a function f is continuous at a point a if the limit of f of x as x approaches a is exactly the value of the function at that point. In this case, we are talking about at a point x which is equal to a. So that's one thing. And this definition now, we can see that continuity itself has three requirements as follows. First, we require the function to be defined. We also require the limit to exist, and the limit of f of x as x approaches a should be the same as the value of the function at x which is equal to a in this case. And remember that we can break the limit into two portions where we have the limit as x approaches a from the left of f of x, where we say for the limit to exist, the left hand limit should be equal to the right hand limit. That means the limit as x approaches a from the right of f of x. So for the function to be continuous, we go a little bit further to say this should be the same as the value of the function at a point a. So that's what we saw previously, and now we are using it now. That's why we're saying you should brush your limits and make sure that you grasp the concept of limit. So what are we saying? So if f is well defined near a, or we can even say in the interval around a, except possibly at a point x which is equal to a, then we say f is discontinuous at a point a. So you can see now it's the opposite of continuity. Or we can put it simple to say f has some discontinuity at x which is equal to a. So that's what we will do. So you're looking at the whole interval now, you pick one point which is a, then we test the continuity there. But if f is not defined at that point, then we'll say f has a discontinuity at x which is equal to a. So one thing which is very important here is geometrical representation of continuity in simple terms or in any formal definition. So we say a function is continuous if we can be able to graph the function without lifting the pen, or you can be able to draw the function without lifting the pen. What are we saying? We are saying, suppose you have your xy plane, and then if you have a function where you start trying to draw the function and you can draw this function without lifting the pen, you see? then we'll say this function is continuous at every point on this function. But we can have other cases. We can have another case where we are still on the xy plane, and then like the Heaviside function that we saw previously, where it had some hole at 0 as we approach from the left of 0. So it remained to be 0 everywhere where x was less than 0. But at x which is equal to 0, if we remember well, the value of the function of the Heaviside function was 1. And it remained at 1 for all values of x which are greater than 0. So if we try to trace this function, you can see when you start from the left, you go over this function. But when you get to 0, it's very difficult to continue drawing without lifting the pen. So you need to jump. Now you jump to 1 and then you start drawing again. You start tracing the function again all the way. In this case, we say f of x is discontinuous at x which is equal to 0. That means at x which is equal to 0, we have some discontinuity for this function. So we couldn't draw it fully without lifting the pen. Another example could be another function of the form, which I'm just drawing here. Suppose you have this function, you try to draw, and then here you skip a gap, and then you start again drawing this function. So the same way with the Heaviside function, you can see here we have some hole here where our function is not defined. So for this point, it means our function has some discontinuity at this point. So our function, suppose our point is a here, so we'll say our function is not continuous at a point x which is equal to a in this case. So keep in mind one thing, we can detect once you are given the graph, looking at if you try to trace the graph whether the function is continuous by just observing the graph without applying the limit. But that's kind of informal. And the formal way to analyze if we are given the function now is to apply the limits and check if the limit of the function as x approaches a, is it the same as the value of the function at a point a. That's things that you should keep in your mind. So look at this example of f of x where we are given a graph of the function, and the question is at which point is f discontinuous, and give some reasons why. So suppose we are using our previous method of trying to draw over the graph, of which may be difficult even to use in the test. But let's see, look at the values of f of x which are less than 1. So you can try to drag your function for values which are less than 1. You come as close as possible. When you get to x which is equal to 1, there is a jump. So you need to jump and then continue again, tracing your function until you get to the left of x which is equal to 3. At x which is equal to 3, we can see the function is defined in this case, but when you go to the right of 3, you need to jump again and then start tracing again from that part. And then when you get to 5, again our function is defined, but it's not the same as the value. It's not, you still need to jump because it's not on the graph in this case. So you can see that the function is defined differently there. So you have a hole on the graph here. So you need to jump when you get close to the left of 5, you jump to this point and then come back to the function and then keep tracing your function all the way. So you can see 3 points that we identified. So we can see some discontinuity at x which is equal to 1, you can see some discontinuity. At x which is equal to 3, you can see another discontinuity at x which is equal to 5. What will differ will be the reasons why at each of these points the function is discontinuous. So at x which is equal to 1, we can see that f of 1 is not defined. So that's the reason for this one. What about at x which is equal to 3? At x which is equal to 3, one thing you can see, the left limit and the right limit are different. So that means the limit as x approaches 3 from the left of f of x is different from the limit as x approaches 3 from the right, meaning our limit does not exist in this case. So since the limit does not exist in this case, therefore we can conclude that the value of the function at this point will not be the same as the limit. So our function is discontinuous at x which is equal to 3. What about at x which is equal to 5? You can see at x is equal to 5, the limit is defined. And the limit as x approaches 5 of f of x is well defined, and the limit is what? Is some point here, which we know that is a positive point. So we can say, let's say it's our b here, so our limit will be just b. But that is different from the value of the function at 5. So that's where the problem is. It's different from the value of the function at 5, which is defined up here, so which is much bigger than b. So that's what will make the difference, the limit not to exist in this case. And these are the reasons which we just defined. You can see we said f of 3 is defined, but the limit does not exist because the sided limits are not the same. And at x which is equal to 5, we also said the limit of f of x as x approaches 5 is different from the value of the function at x which is equal to 5. So those are the reasons why we say the limit does not exist in this case. Now, here are other examples, 3 examples in this case. And then the question is, where are each of the following functions discontinuous? Number A, you can already see that it's not defined at x which is equal to 2. So we already suspect that this point might be a discontinuous where the function is not continuous at this point. Number B, you can see that the function is well defined at x which is equal to 2. And also number C, the function is defined at x which is equal to 2 and the value of the function at x which is equal to 0. And the value of the function at x which is equal to 0 is 1. And also here the value of the function, number B, at x which is equal to 2 is 1. So now what remains as the question is whether the value of the function is it the same as the limit of the function at x which is equal to 2. That's one thing. So we have concluded that for number A, f of 2 is not defined. Therefore, f is discontinuous at a point x which is equal to 2 in this case. And then we come to the next case. You try to find the limit for the next case. Then you simplify a function, you factorize, and then you simplify a function, you get here. You get as the limit of this function as x goes to 2, it becomes 3. So in this case, again, since remember on the right hand side we find that f of 2 was 1, so this is different from f of 2 which was equal to 1. Therefore, I'll say the limit does not exist. The limit exists, but the function is not continuous. The limit exists, but the function is not continuous at x which is equal to 2 because the value of the function is not the same as the limit. So we'll conclude that f is not continuous at x which is equal to 2. just because the value of the function is not the same as the limit. And then number C. Number C, the limit of the function, you can see here as we approach 0. From the left, you will, or from the right or right, you end up with an infinity, which is completely different from 1. Again, we conclude that f is discontinuous at a point x which is equal to 0 in this case. So, we introduce another term here, removable discontinuity. So, we will say a function, which you can see is our straight line that we ended up with from the right side, where we had x plus 1 after we simplify our function. So if you draw that straight line, you have this straight line, but you still remember that the function before simplification was not defined at x which is equal to 2. So at x which is equal to 2, we still have a hole here to show that the function is not defined. But we can redefine this function such that the function is continuous at this point. We can redefine this function, especially piecewise. An example is here where we still have a removable discontinuity, where we redefine our function but with a value of 1 at this point. But suppose we redefine our function such that we say at x which is equal to 2, we redefine our piecewise function such that f of 2 is nothing but 3. Then, in this case, our function will be continuous. So now that it is possible to redefine our function such that we can remove a discontinuity, we will say this function has a removable discontinuity. And also this one has a removable discontinuity, because if we can redefine our function, we can get a continuous function. Another example here, remember we had f of x being equals to 1 over x squared, and also f of 0 was defined to be 1. So f of 0 is 1 here, but you can see as we approach 0, the limit from both sides, the limit of f of x is infinity. So the function approaches infinity as we get closer and closer to 0 from both sides. So it approaches infinity. So in this case, we have a discontinuity, an infinite discontinuity. So look at this number d, which we have not even given as an example, but is a good answer here, which gives an idea of another type of discontinuity. So suppose you want to trace this function. If we try to move along this function, when you get to, although I'm not exactly, actually I should trace it on top of this graph. When you get to x which is equal to 0, you need to jump again and then start tracing from here. And then when you get to x which is equal to 1, you need to jump again and then start tracing again here. And then you jump again when we get to x which is equal to 2, and then start tracing, you jump again when we get to x which is equal to 3. In this case, we'll say our function has some jump discontinuity. And there are so many at x which is equal to 0, at x which is equal to 1, at x equal to 2, many of them. So these ones, we call them a jump discontinuity. So that's what we have just concluded, that if our function has can be redefined such that we can remove a discontinuity, then we say we have a removable discontinuity at that point. And then we agreed that if we can, on our previous example, if we can redefine f such that it becomes 3 at x which is equal to 2, then we finally get a continuous function. That means we have removed the discontinuity. So that is a removable discontinuity. We also saw that we had an infinite discontinuity where our function was blowing up to infinity as we get closer and closer to 0. And also we also saw number d, that we had jump discontinuity, a lot of jump discontinuity. So that brings us to a definition of sided continuity like we did with limit. So for sided continuity, we look at decided limit. In this case, we are looking at the right-hand continuity. So we say a function f is continuous from the right at a point a if the limit of f of x as x approaches a from the right is the same as the value of the function at that point. So here we are looking at decided limit. And the same thing can be said about the left-hand limit. F is continuous from the left at a point A if the limit of f of x as x approaches a from the left is the same as the value of the function at that point A. This is what we will say. And we give another definition here where we look at that f of x is continuous on an interval if it is continuous at every point in that interval. So now, this is very tricky because all along we have been talking about continuity at one point and discontinuity at one point. Now we extend a little bit to an interval. And imagine if we are to test every point of the interval. So you see it will be a little bit challenging. So as we go along, we'll see some of the definitions that will simplify our work, or definition or a theorem that will simplify our work, so that we don't need to do too much work. Properties of a continuous functions. So let's look at some properties of continuity. First, let's assume that, looking at this theorem, let's assume that f and g are two continuous functions at a point x which is equal to a, and c is some constant. Then the following functions which are made from these functions are continuous at x which is equal to a. If you take you create another function which is built from the sum of the two functions, that function will be continuous at x which is equal to a. You take a difference, you still find a continuous function. You take a product, you still find a continuous function. You get a quotient where you assume g of g is different from 0, then you still get a continuous function. You multiply one of the function by a constant, then you still get a continuous function. But one thing bear in mind, all these depend on the assumption that f and g are continuous at x which is equal to a. If f and g we are not told any information about them, we cannot conclude that the sum of the two functions are continuous or the product. We will only conclude because we are already told that they are already continuous at a point x which is equal to a. And we can extend that theorem to an interval, now not considering a, such that the sum and the product and the constant multiple of the function, and then the product, they are still, and quotient, they are still continuous at that point. Which brings us to a good one theorem that is going to help us a lot. Remember, we talked about trying to show at each point of the interval that the function is continuous is a lot of work. Now here is the theorem which says any polynomial is continuous everywhere. That is continuous if you are looking at a function of one variable is continuous from minus infinity to infinity. So this is good because it means if we have a function that is a polynomial, you can quickly conclude from this theorem. And another part of the theorem says any rational function is continuous everywhere where it is defined. That is, it is continuous in its domain. This is another good thing now. Even if somebody gives you a piecewise function which is built from a polynomial plus a rational function, that means each piece of the interval is defined a polynomial or a rational function. So you can only target where the two intervals join each other. That means you can easily conclude in each interval that since here I have a polynomial, by this theorem, a polynomial is continuous everywhere on its domain. And then since this portion of interval, I have a rational function is continuous wherever it is defined. So the only interesting point is where the two functions come together, whether that point is still a continuous, or whether at that point the function is still continuous. That will be the main question that you need to address. So from those theorem, we can also remember that the formula for the volume of a sphere is defined by a polynomial function v, which depends on r, where we can make our sphere as big as we want by changing the value of r. So this is a polynomial and it's a continuous function. That means it's well defined. So it means we can make our sphere as big as we want. And another example is if a ball is thrown vertically into the air with a velocity of 50 feet per second, then the height of the ball in feet after t seconds is defined by this formula, which is still a polynomial somehow. You can see it's a polynomial of degree 2. So this polynomial is also continuous here. So we can make that height as big as possible or as small as possible. So now it will be the matter of interpretation. Now we are talking about the height. Can it be negative? Can it be what? But we can always, that function is well defined on its domain. It's well defined as a polynomial. So let's look at another example here where we have to find the limit. Now we want to apply that theorem indirectly. So suppose somebody gives you this and then asks you to find the limit of this function. And then first you may start trying to factorize, which you may do a lot of work for nothing. But now the best way is to first test where is this function continuous. So it will be, it's a rational function, it will be continuous on its domain, which means everywhere except at x, which is equal to 5/3. And you can see quickly that -2 is not included in the denominator. It's not a point that gives us a problem in the denominator. So straight away, you can do a direct substitution and then find f of -2 and then finally get to a limit as this one. I know people could have struggled and then start thinking about how to factorize the numerator such that 5 minus 3x start cancelling, which may not be the case. It may be simpler than you think. As you can see, this one is much simpler. So before you start tackling a problem, treat each problem or each case separately and individually and try to be as simple as possible. Now, we can even extend our idea of continuity to trigonometric functions, especially looking at a sine function and a cosine function. Remember, every point on a circle can be defined as r cos theta, r sine theta. So every point on a circle can be defined. Now, if we take our r to be equal to 1, assuming we are on a unit circle, then our point everywhere on the circle is defined by this function. And you can see on that unit circle, the limit as theta goes to 0 of cosine, it goes to 1, and sine goes to 0. So that's one thing that you recognize, and then we can conclude that the limit of cos of theta as theta goes to 0 is 1, and the limit of sine of theta as theta goes to 0 is 0 in this case. And we can use that to build up more complicated trigonometric functions. For instance, let's look at a tangent function, which we can split it into sine over cosine. Now, here you can see, because now you have written it as a quotient, you can see that there is a problem somewhere, especially where the denominator is 0. That means where cosine of x is 0, this function will not be defined. That means, so our function is continuous everywhere except where cosine x is equal to 0, because we are dividing by cosine. That's one thing you should take from here. But where is cosine? Cosine of x being 0. So we are saying this will happen anywhere where x is an odd multiple of pi over 2. What are we saying? We are saying anywhere where we can write x to be equal to either plus or minus, you can say 2n plus 1 times pi over 2. And then let your n now to be an integer. In fact, since we have introduced plus or minus there, you can make your n to be an integer, be inside the integer plus 0. So you can say positive integer plus a set of 0, which contains only 0. So it means at 0 you have plus or minus pi over 2. At 1, what do you have? At 1 you have 3 plus or minus 3 pi over 2. At 2 you have plus or minus 5 pi over 2. You can continue listing all of them. There are so many you cannot finish. So that's why we have a tangent graph here having some vertical asymptote at x, which is equal to pi over 2 or minus pi over 2, is also having some vertical asymptote at minus 3 pi over 2 and also at 3 pi over 2. This is just an example that gives you an idea, but the vertical asymptote for a function tan of x, there are so many, you cannot exhaust them. That's why we say it has some infinite discontinuity. Infinite discontinuity. There are so many, you cannot finish them. So you can keep listing them using this formula. You will not finish them. So this is what you should be aware of. And then use them. And we are trying to get to different examples. Remember, we started with a polynomial, we went to rational, now we are to trigonometric. So, Theorem 7 tries to bring all these things together. So, the following types of functions are continuous at every point in their domain. So, it could be polynomials, and remember, rational functions wherever they are defined, and also root functions wherever they are defined, and also trigonometric functions wherever they are defined. And that brings us to talk about now one last example probably that we haven't touched, or a theorem that can address the issue of composite function, a function that is built with another function. So first, suppose that f of x is continuous at point x which is equal to b, and the limit of g of x as x goes to a is b. So then we can conclude straight away that the limit of f of g of x is equal to f of b. Or in other words, we can say the limit of f of g of x is the same as passing the limit into f. Then we have f of the limit of g of x, and we know that the limit of g of x is nothing but b, so we are left with nothing but f of b. So this is how you compute the limit now for composite function. But remember, the assumption is that f of x is continuous, f is continuous at b, and also the limit of g also exists and is b as x goes to a. Then you can be able to find the limit of f of x as x approaches a. That's one thing that you bear in mind as you work this problem. So in general, we can say if g is continuous at a and f is continuous at g of a, then the composite function, this one given by f of g of x, is continuous at the point x which is equal to a. That's one thing you should bear in mind. So today we had a very long lesson, and what did you learn today? You learned about continuity, and we also touched different types of functions where you can deduce continuity easily. We started with a continuity at one point, and then we extended continuity a little bit to an interval. We even extended to the domain of the function. We look at types of function like polynomial, rational function, trigonometric, and a root function, together with a composite functions. So we're able to see how we can deduce the limits of the continuity of these functions. And also remember that we said we through these theorems that we just went through, you can use these theorems to conclude the limit at other points instead of proving the limit at every point of the domain, where you may take the whole day or the whole night, even the whole year, or the rest of your life trying to prove the limit of the function. So let's stop here and meet next time. Hope you are still catching up well. Good luck.